Welcome to this tutorial on model-based design for Quadcopter Autopilot, from concept to prototype. Here is the outline of this tutorial. In this session, we're designing the flight control laws for a quadcopter. We'll build and explore the flight control, control allocation, and motor command subsystems using Simulink. Let's recap the functional requirements we covered in Session 2. Stabilized mode. The autopilot helps stabilize the drone's roll, pitch, and yaw, but the operator is responsible for controlling altitude and position. It provides basic stabilization for manual flight. Altitude mode. Here, the autopilot maintains the drone's altitude by adjusting throttle, while the operator controls the roll, pitch, and yaw. It reduces the pilot's workload by keeping the drone at a constant altitude. Position mode. In this mode, the autopilot holds both the horizontal position, altitude, and heading, allowing the operator to focus on adjusting the roll, pitch, and yaw. Trajectory mode. The autopilot follows a predefined path consisting of a sequence of spatial points with timestamps. In a quadcopter autopilot design, functional requirements define what the system must achieve, and these requirements directly shape the system architecture into logical modules like flight management, control, and sensor fusion. The architecture ensures all requirements are addressed systematically. Flight control laws, such as rate, attitude, and position controllers, implement the functional requirements and fit within the system architecture, ensuring consistent behavior. Using a model-centric approach, we capture requirements, architecture, and control law within models from the start. These models serve as a single source of truth, enabling early validation, fast iterations, and seamless traceability from requirements to implementation, improving design quality and reducing development risks. Here is the control architecture modeled in Simulink. We'll walk through it step by step. First, let's begin with the motor command subsystem. The motor command subsystem processes motor control signals based on the selected flight mode. It takes 4 motor command inputs, representing desired motor speeds, and determines the corresponding outputs based on the flight mode. This shows the implementation in Simulink. The inputs of the desired motor speeds are generated by the flight control system, while the outputs of the adjusted motor commands are based on the flight mode. The flight mode signal comes from the flight management subsystem. Examples of the flight modes include disarmed mode. All motor commands are set to 0, ensuring no motor activity. Armed mode. Motors respond to control inputs, allowing the quadcopter to take off, hover, and maneuver. And it receives commands from the control allocation subsystem for stabilized mode, altitude mode, position mode, and trajectory mode. Next, we will explore the control allocation subsystem. The control allocation subsystem, also known as the mixer, is responsible for distributing the desired control efforts, thrust, roll, pitch, and yaw moments, to the individual motors of a quadcopter. This subsystem translates the high-level control commands from the flight control law into specific motor commands that achieve the desired vehicle motion. This shows the implementation in Simulink. For a quadcopter, control allocation is typically handled using an effective matrix, which maps the desired forces and moments, such as roll, pitch, yaw, and thrust, to individual motor commands. This matrix captures how each motor contributes to the overall motion of the vehicle. By inverting or pseudo-inverting this matrix, we can calculate the necessary motor commands to achieve the desired dynamics, while respecting actuator constraints. Multicopters come in various airframe types. While the quadcopter is the most common, other types include hexacopters, octocopters, and their variations. Each airframe configuration has a corresponding effective matrix that describes how individual rotor thrusts contribute to the total forces and moments acting on the vehicle. Note that the effective matrices shown here primarily account for the rotational directions of the propellers. In practice, The exact structure of the matrix depends on additional factors, including the number of motors, their placement angles relative to the airframe, and the spin directions, clockwise or counterclockwise, of each rotor. These factors collectively determine how individual motor thrusts contribute to the total forces and torques generated by the vehicle. Multicopters are typically fully actuated or even over-actuated systems, depending on the number of motors relative to the number of control objectives: thrust, roll, pitch, and yaw. For example, hexacopters and octocopters are over-actuated, meaning they have more actuators than strictly required to control the vehicle. This redundancy introduces flexibility in the control allocation process, allowing the system to pursue optimized control strategies, such as minimizing energy consumption, reducing mechanical stress, balancing thermal loads, or even improving overall efficiency. More importantly, redundancy plays a critical role in enhancing the fail-safe and fail-operational capabilities of the system. Over-actuated multicopters can dynamically redistribute the required forces and moments among the remaining healthy motors after a failure. This is typically achieved by resolving the control allocation problem under new actuator constraints in real time. Designing an effective redundancy management strategy is a critical step for multicopters intended for high-reliability applications, such as delivery drones, inspection drones, or emergency response UAVs. All right, let's move on to the flight control subsystem. Based on the flight dynamics of a quadcopter, the control laws are organized into two main sections: horizontal control and vertical control. The horizontal control manages either the rotational dynamics around the roll, pitch, and yaw axes, or the horizontal velocities, ensuring stable attitude, orientation, and horizontal movement. The vertical control governs motion along the thrust axis, controlling altitude and vertical velocity. This separation allows for a clearer architecture of the control loops and simplifies the overall control design. How does this architecture address the functional requirements for the 4 flight modes? The flight control architecture is designed hierarchically to support increasing levels of autonomy and control authority across 4 main flight modes. Stabilized mode includes the core low-level control loops: attitude control, Euler rate to angular rate conversion, angular rate control, and vertical velocity control. This mode ensures the vehicle remains stable and responds directly to pilot inputs or reference commands for orientation and altitude rate. Altitude mode builds upon stabilized mode by adding altitude control. It introduces a feedback loop to maintain or track a desired altitude, enabling the vehicle to automatically regulate vertical position while still relying on pilot input for horizontal movement. Position mode adds horizontal control layers on top of altitude mode. It includes horizontal velocity control and horizontal position control, enabling the vehicle to autonomously maintain or track desired positions in the XY plane. Trajectory mode further extends the architecture by incorporating yaw angle control, allowing for precise orientation tracking during trajectory-following missions or autonomous path execution. This modular control structure allows for progressive layering of functionality while maintaining robustness and clarity in design, making it easier to tune and verify individual control components at each mode of operation. Let's look into the vertical control subsystem. This control loop regulates the vehicle's motion along the vertical thrust axis, specifically tracking the velocity down command, typically provided by higher-level controllers or the pilot. A PID controller is used to minimize the error between the commanded and actual vertical velocities. To ensure accurate thrust control, especially during tilted flight, the controller includes roll and pitch angle compensation. This accounts for the fact that, when the vehicle is not level, part of the thrust contributes to horizontal motion, reducing the effective vertical force. The output of the vertical velocity controller is a thrust command, which is then passed to the control allocation block. This thrust value ensures the desired vertical speed is achieved, regardless of the vehicle's orientation. Similarly, the altitude control subsystem uses a PID controller to track the altitude z-axis command in the NED coordinate frame. It compares the desired altitude with the measured altitude and computes a velocity down command as its output. By separating altitude and velocity control into two cascaded loops, the system gains improved stability and responsiveness, with each loop tuned for its specific dynamic range. All right, let's now transition to the horizontal control. Let's begin with the angular rate control, which regulates the rotational speeds around the roll and pitch axes. This loop receives desired angular rates from the attitude controller and uses a PID controller for each axis to minimize the error between the commanded and measured angular rates. The PID controllers compute the required torques that need to be applied about each body axis to achieve the target angular rates. The Euler rate to angular rate conversion is an important concept in 3D rotational kinematics. Euler angles describe orientation. However, their time derivatives, often called Euler rates, do not directly represent angular velocity in the body frame. To obtain the true angular velocity vector in the body frame, we need to convert Euler rates using a transformation matrix that depends on the current Euler angles. Attitude control. The goal of attitude control is to stabilize and command the orientation of the quadcopter by regulating the roll and pitch angles. This allows the quadcopter to hover level, tilt forward or backward, pitch, or sideways, roll, for translational motion. Horizontal velocity control. The horizontal velocity controller regulates the quadcopter's motion in the XY plane, forward, backward, and left-right movement, by controlling velocity x and y. The controller generates the desired attitude, specifically roll and pitch angles commands. Horizontal position control. The horizontal position control loop governs the quadcopter's movement in the x and y directions of the NED frame. A PID controller is used on each axis to reduce the position error and generate the desired horizontal velocity commands. Horizontal position control is crucial for autonomous navigation, waypoint following, and precision hover tasks. Yaw angle control. The yaw angle control loop governs the quadcopter's heading or orientation around the vertical, Z, axis. It receives a desired yaw angle and compares it with the current yaw angle. A PID controller is used to minimize the yaw angle error and generate a desired yaw rate, angular velocity around the Z-axis. Unlike roll and pitch, yaw control does not directly affect translational motion, but is essential for maintaining directional awareness, coordinating flight paths, and aligning the vehicle during tasks like trajectory following or visual targeting. All right, we've now walked through all the major subsystems of the flight controller. At this point, you might be wondering, how do we actually design and tune the PID controllers that power these control loops? To illustrate the process, we'll take the attitude control subsystem as an example. Specifically, we'll demonstrate how to fine-tune the proportional, integral, and derivative gains to achieve the desired performance. Let's take a look at the control design workflow. The quadcopter model is complex, with many nonlinear components. So the first step in the process is to trim the model to identify a steady-state operating point. An operating point refers to a specific set of values for the state variables, like position, velocity, and orientation, and control inputs, such as thrust and control surface deflections, that represent a steady flight condition. This steady state is crucial as it serves as the baseline for further analysis and control design. Once we've got the operating point, we can then linearize the model around this point. Linearization involves approximating the nonlinear system with a linear model, which simplifies the design and analysis process, making it possible to apply classical control techniques. With the linearized system in hand, we can now proceed with classical control design, such as PID controllers, using the system's transfer functions or state space representations. This allows us to design a controller that works well within the linear approximation of the system. After the controller design is complete, we move to the final step, verification. We validate the controller's performance by testing it with the original nonlinear model to ensure it maintains stability and achieves the desired performance under realistic operating conditions, where the linear assumptions may no longer hold. Now we will demonstrate how these steps can be carried out in Simulink. In this demonstration, we'll show how to trim, linearize, design, and implement an altitude PID controller for a quadcopter model in Simulink. First, we need to specify the linear analysis points. In this case, we define the velocity down command as an input perturbation and the altitude z as an output measurement. Once the analysis points are set, we'll open the Model Linearizer app from the Apps tab. Using this app, we can perform both trimming and linearization of the model. To begin, we open Model Initial Condition and select Trim Model. This view displays all the states, inputs, and outputs of the model. In our case, we want the velocity down to reach a steady state, specifically trimmed at 0. Let's go ahead and trim the model with these specifications. After trimming, a new operating point, optrim1, is created. When we inspect this variable, we can see that the desired state derivatives are all zeros and the actual derivatives for those states are very small, confirming that we have found a valid trim point. Next, we'll linearize the model around this operating point. To do this, we simply select the linearization input and output signals we previously defined. Now let's linearize the model and compute its step response. The linearized system is generated as linsys1. We can export linsys1 to MATLAB workspace for control design. Viewing it as a transfer function, we notice it's relatively complex with multiple poles and zeros. To simplify the system for easier controller design and implementation, we use the minreal command to cancel pole zero pairs and reduce the system order. Now we move on to the Control System Designer app. This app is ideal for designing controllers for single input, single output SISO systems like ours. It provides graphical and automated tuning tools such as root locus, Bode plots, and PID tuning. By default, it opens with the Bode editor, root locus editor, and step response plots. Inside the app, we'll see 4 elements in the control loop: F, C, G, and H, where C represents the controller. We can review or modify the control architecture by selecting Edit Architecture. For controller tuning, we expand the Tuning Methods tab, which lists several methods. In this demonstration, we'll choose PID tuning. Tuning can be done either in the time domain or the frequency domain. After tuning the controller, we can review its performance and design parameters. Finally, we can generate a Simulink model with the tuned block values. When we run the simulation, the step response matches exactly with the one we observed in the Control System Designer app. Another approach to designing a PID controller is to use the PID controller block, which provides a fast and broadly applicable method for single-loop PID tuning. First, we change the controller parameter source from external to internal. Then, we launch the PID Tuner. When the PID Tuner opens, it automatically computes a linearized plant model based on the plant input and output signals identified by the controller, using the current operating point for linearization. Next, we can tune the controller by manually adjusting the design criteria in 2 available design modes. The PID tuner then calculates controller parameters that robustly stabilize the system according to the specified criteria. Once the tuning is complete, we export the tuned parameters back to the PID controller block, and verify the controller's performance by running a simulation in Simulink. If we want the tool to automatically optimize parameters to meet specific design requirements, we can use the Response Optimizer app. Let's walk through an example where we optimize the proportional gain Kp. First, we replace the constant gain with a variable named Kp, setting its initial value to 1. To launch the app, go to the Apps tab, and under Control Systems, select Response Optimizer. Once the app opens, the first step is to specify the design variables. Here, we add Kp to the design variable set and define its minimum and maximum bounds. Next, we specify the design requirements. The Response Optimizer provides various types of requirements. For this example, we select Step Response Requirements. We choose altitude h as the response signal and define the requirement. For instance, setting the rise time to 1.5 seconds. The step response envelope will then be visualized in the figure, showing the target performance bounds. Now we can start the optimization process. The optimization progress report shows that the solver successfully found a solution that meets the design requirements within the specified tolerances and parameter bounds. As shown in the figure, the optimized step response lies within the white region defined by the design requirements, indicating that all specifications are satisfied. To view the optimized parameter values, simply click Design Vars. Let's take it a step further. This time, we lower the rise time requirement from 1.5 seconds to 1 second and rerun the optimization. In this case, the optimizer fails to find a solution that meets the tighter requirement. One way to address this is to adjust the design variable bounds. Specifically, we increase the maximum value of Kp from 1.5 to 2.5. After updating the bounds, we rerun the optimization. This time, the optimizer successfully finds a solution. The new optimized value for Kp is approximately 1.6, just slightly above the previous maximum limit of 1.5. Now that we've walked through the control design workflow step by step, we have a clear understanding of how to approach the design, from trimming and linearizing the model to applying classical control techniques and verifying the results. Note that the operating point does not necessarily mean the quadcopter is in a fixed position. It could correspond to other steady conditions such as a fixed velocity, fixed angular velocity, or a specific altitude. Therefore, there are many potential operating points, each corresponding to different flight conditions. To manage these varying conditions, multiple controllers might be needed to handle the different operating points. In this case, gain scheduling becomes useful. Gain scheduling allows the controller gains to vary depending on the current operating point, ensuring optimal performance across a wide range of flight conditions. PID control is often considered the baseline flight control algorithm due to its simplicity and effectiveness in many flight scenarios. However, as the complexity of the system increases or the need for higher performance grows, more advanced control algorithms can be used. Some of these include Model Predictive Control, MPC, Linear Quadratic Regulator, LQR, Linear Quadratic Gaussian, LQG, Adaptive Control, Nonlinear Backstepping, Sliding Mode Control, Geometric Control in SO3, Learning-Based Control, such as Reinforcement Learning. Each of these methods offers unique advantages depending on the flight requirements, system complexity, and the level of performance needed. Last but not least, there are several important considerations to keep in mind when developing a flight control law. Smooth transitions between flight modes, to avoid abrupt changes in control behavior that may destabilize the vehicle. Integrator reset strategies, especially during mode switching or manual override, to prevent integral windup and ensure stable recovery. Sensor and actuator calibration, which is essential for accurate state estimation and precise control. Airframe oscillations, which may arise from high control gains or structural flexibility, requiring appropriate damping or filtering. Actuator saturation, where motor or servo limits can lead to degraded control performance or instability if not properly handled. Safety and fail-safe mechanisms, including redundancy and emergency landing protocols, to ensure operational reliability. Energy efficiency, optimizing control inputs to minimize power consumption while maintaining performance. Adaptation to payload changes, as added or removed loads alter the dynamics and may require controller adjustments. Real-time system monitoring and diagnostics, enabling health checks, fault detection, and maintenance planning. These factors play a critical role in designing a robust, safe, and high-performance flight control system. All right, let's wrap up this session. We have now covered the three key subsystems of the Autopilot: motor command, control allocation, and flight control subsystems. I hope this session provided you with a clear understanding of flight control law design in Simulink. In the next session, we will focus on flight management design. I look forward to your participation.